Today we're going to start talking about distributions. And when we start talking about distributions, you'll see that they already seem pretty familiar. What do I mean by a distribution? Well, we're going to start with the model of a distribution by talking about putting balls into boxes. We'll say we distribute the balls into the boxes. And we'll ask the question, how many ways can we do this? How many ways are there to distribute distinct objects? This will be, at first we'll talk about distinct objects into distinct boxes. So here's the ball into boxes example. Let's say we have 7 balls. So I'll just label them here, 1, 2, 3, 4, 5, 6, and 7. And they're labeled 1 through 7, so these balls are all distinct from each other. And they're going to go into, say, three boxes. And I'll use this, just like the book does, to denote boxes. And we're going to assume the boxes are distinct. Say the boxes have labels A, B, and C, or maybe they're just in separate locations that are distinct, which would make a difference which box a particular ball goes into. And we ask, how many ways can we put the balls into the boxes? Well, I'll show you one way to do it. You put 1 in there, you put 2 in there, you put 3 in here, you put 4 in here, you put 5 in here, you put 6 in here, and then maybe you put 7 in here. That's one way to do it. There are, of course, many, many other ways to do it. Is it easy to count how many ways you can do this? Sure, we just use the product rule. We ask how many choices do we have for where to put ball 1? Well, we have 3 choices. How many choices do we have for where to put ball 2? We have 3 choices. For ball 3, we have 3 choices. For ball 4, we have 3 choices. For ball 5, we have 3 choices. I think you see the pattern here. For ball 6, we have 3 choices. And for ball 7, we have 3 choices. And we put that all together, we get 3 to the 7th ways to create a distribution of 7 balls, 7 distinct balls into 3 distinct boxes. Now, you don't always have to talk about balls and boxes. I could ask, how many ways can we assign one of 3 different rooms to 7 people? So you have 7 people, and they have to be put into 3 different rooms. How many ways can you do that? Of course, the answer is the exact same, 3 to the 7th, for the exact same reason. This is in the book, standard problem number 8. The number of ways to distribute m distinct balls into n distinct boxes is n to the m. Now, this should look familiar. This is very much like problem 1 when we counted strings. In fact, the number of strings from problem 1, I'll just write SP number 1 here, the number of strings of length. Here I'll use m for the length. In standard problem number 1, they call it k, but let's say we called it m. The number of strings of length m from an alphabet, say an n-letter alphabet, is n to the m. Are the answers just the same by coincidence? No. There's a very simple one-to-one correspondence between distributions of m distinct balls into n distinct boxes and strings of length m from an n-letter alphabet. I'll show you just with a simpler example. Let's say we're talking about 4 balls going into 3 boxes. So if we have 4 balls going to 3 boxes, so m equals 4, and of course here n will be 3. There are lots of ways to do this, so I will just create one here. I say there's a one-to-one correspondence between such distributions and 4-letter strings. What is the natural correspondence? Well, you can think of the letters in the alphabet. That's why we're using n equals 3 to denote the boxes here as the labels on the boxes. So here, think of the alphabet. It's just A, B, C. We had 4 distinct balls. Think of the balls representing the spaces in the string, the positions, 1, 2, 3, and 4. And saying ball 1 goes into box C is like putting a C in position 1. Ball 2 goes into B is like having a B. 3 goes into B, so that's like a B here, and then an A. And you see, any distribution of balls would lead to a different string, and vice versa. The problems are really the same problems, just in different language, and of course they have the same answer. So now we want to change the problem a little bit and ask, what if instead of distributing distinct objects like distinct balls that are numbered, we distribute identical objects into distinct boxes? So here's the example we'll look at. How many ways can we put 7 baseballs into 3 boxes? And here when I say 7 baseballs, I'm just assuming they're all generic baseballs. It's not that the individual balls are identical to each other in the sense of physics. They're different particles. They might have different scratches or whatever. But as far as anybody cares, a baseball is a baseball. The only thing you would care about is how many balls go into each box. So for all practical purposes, they're identical, and we want to count the number of ways we can put them into boxes where the only thing we care about is how many balls, not which ones they are. So how would we do that? Well, we'll model it like this. We have 7 balls, and they all look the same. And they go into 3 boxes. I'm going to put the boxes like this. The boxes are distinct here. They're labeled, say, A, B, and C. Well, I can give you an example of a distribution. But with all of these arrows showing the distribution, what is the only thing that matters? The only thing that matters is there are 3 balls in box A, 2 balls in box B, and 2 balls in box C. So even to get the answer here, I want to say this problem is just like the problem we dealt with when we were counting combinations that allow repetitions. Why? Because I want to talk about a one-to-one correspondence between distributions of identical balls into distinct boxes and combinations where repetitions are allowed. And here we need 7, so I didn't leave myself enough space. Here's length 7. I want a combination. Repetitions allowed. And so this distribution of identical balls into the boxes A, B, and C would be like the combination A, B, B, C, C. In other words, just a combination that has 3 A's, 2 B's, and 2 C's. It doesn't matter what order I write that in. And you can see any distribution of identical balls into distinct boxes can be mapped to a combination like this, and vice versa. And we know how to count the number of combinations of length 7 from a 3-letter alphabet. That number, and I think this is standard problem 6 probably, is well, for the combinations, we call the number, in this case, 3, choose 7. We want combinations of length 7 from a 3-letter alphabet with repetitions allowed. And we know how to evaluate 3, choose 7. We can write that as the regular combination number, 9, choose 7, which is the same as, of course, 9, choose 2, which is 9 times 8 over 2, which is 36. So there are 36 ways to do this. So we create the standard problem number 8, which asks, how many ways are there to distribute m identical balls into n distinct boxes? And just as we saw before, the answer is n choose m with repetitions, just as it is for counting combinations of length m from an n-letter alphabet. with repetitions allowed, and that's n plus m minus 1, choose m. And you see there are lots of problems where we can think of the things being distributed as identical. I think I mentioned one in class, to at least one of the sections, probably maybe both. But here, I'll state it again, the problem. Let's say I have 3 $100 bills, and I have 30 students in class, and I want to pick a way to give out the 3 $100 bills. Well, if I choose to give out the $100 bills and I allow repetitions, that means one person might get 2 of the $100 bills. One person might get 3 of the $100 bills, and nobody else gets anything. Or I might choose 3 different people to give the $300 bills to. How many ways can I give out 3 identical $100 bills? And when I say identical $100 bills, I don't even have to say identical. How many ways can I give out $300 bills to students in a 30-person class? Unless one says there's something bizarre and special about these $100 bills, they're for all practical purposes identical. Well, the answer will be, what is it, 30, choose 3, with repetitions allowed. I want combinations of length 3 from the 30-letter alphabet. The 30-letter alphabet would be the 30 different people. And I have to choose a combination of length 3 where repetitions in this case would be allowed. So this is standard problem 8. We can think of it as distributions of identical balls into distinct boxes or combinations with repetitions allowed. And of course we can write that as 32, choose 3.